Alright guys, happy snow day number 2. We're back. We're going to start with an example problem. The example problem says, calculate gravitational force between the sun and the earth. Alright, the mass of the sun is 2 times 10 to the 30 kilograms, and the mass of the earth is 6 times 10 to the 24 kilograms. The distance between the sun and the earth is 1.44 times 10 to the 11th meters. Right? So it's asking you for the gravitational force. So use the equation that we gathered last video. Force of gravity equals Gm1 m2 over r squared, which would give us 6.67 times 10 to the negative 11. It's going to get really tight. Times 2 times 10 to the 30 times 6 times 10 to the 24, all over 1.44 times 10 to the 11th squared. Beautiful. Doing the math, you should figure out that the force of attraction between the sun and earth is 4.1 times 10 to the 22 newtons. It's a lot of force. Cool. Pretty simple. Moving on to our notes for today. Stay tuned for a little bit of a surprise here a little later in the video. So our second notes. This note set is gravitational potential energy. And we've learned this before. We've said UG equals MGH. Alright, but that's for the potential, gravitational potential energy on Earth, right? So the universal gravitational potential energy is Gm1 m2 over R. Only difference here is it's negative. If we're drawing a picture of this, we have, say, the big mass here, and the smaller mass here, and the distance between them is r. So the idea here is that the potential energy at r equals infinity, right? If r equals infinity, you're dividing by a really big number, and so gravitational potential energy at infinity is 0. That's indefinitely far away. Indefinitely far. Okay, so that's really all for the notes. Let's do a practice problem. So we have a planet, and that planet is Earth, and we have a rock that is currently 2,000, it's 2,000 kilograms. And it is 7.2 times 10 to the 6th meters away. The radius of Earth equals 6 times 0.4 times 10 to the 6th meters. The mass of Earth is 6 times 10 to the 24 kilograms. Cool. So what I want you to do is to find potential energy when R equals 7.2 times 10 to the 6th meters away. Cool. So we just plug this into our equation. Potential energy equals G M1 M2 over R. Don't forget the negative sign. Alright, so potential energy at 7,200 at 7.2 equals negative 6.67 times 10 to the negative 11 times 2,000 times 6 times 10 to the 24 all over 7.2 times 10 to the 6th UG at 7.2 times 10 to the 6th equals, doing your math right, you should get negative 1.11 times 10 to the 11th joules. Alright, so now we're gonna try and do B. What is the find when we are 5,000 kilometers away, or that is equal to 5 million meters away. Alright, so again, and this is when we're 5 million meters above the surface. Alright, so this time we're 5 million meters above the surface, so that's 5 million plus the radius of Earth. Alright, so we do universal gravitational potential equals negative 6.67 times 10 to the negative 11 times mass 1, 2,000, times mass 2, which is 6 times 10 to the 24, all over the radius. And the radius this time is our 6.4 times 10 to the 6th. And adding that to the 5 times 10 to the 6th right here, 5 times 10 to the 6th. All right, so now we're a ways higher. This isn't very high up above the ground up here. Now we're going higher or farther away. The potential energy at, let's call it, this would be 11.4 times 10 to the 6th, so bigger, farther away, equals, you should get negative 7.02 times 10 to the 10th joules. Notice how that's less, right? Because remember, the further you go away, the less potential energy you have. All right, so remember these two numbers. 7.2 is negative 11, or 1.11 times 10 to the 11th, and UG at 11.4 is negative 7.02 times 10 to the 10. If you're watching this and you want a little bit of extra credit, email me a joke and the time that you are watching the video, and I will get you some extra credit. If you make me laugh, I'll give you an extra point. Go. Part C. Part C is what is the work required to move rock from 5,000 kilometers, that was part B, what we just calculated, to a distance of r equals infinity, or really, really far away. All right, so now you have Earth, and all the way over here is, so right here at 5,000 kilometers, and then all the way out here at r equals infinity, you have, oh yeah, that's the rock. R equals infinity, you have some potential energy equal to 0, we said. And we just calculated in part B, that the potential energy here was UG equals negative 7.02 times 10 to the negative, or 10 to the 10. So doing our big physics equation that we've done in the past, energy initial plus or minus work equals energy final. And if our initial energy is here, you have negative 7.02 times 10 to the 10 plus or minus work equals your final, which is 0. Subtract or add this number over to the other side, you get plus or minus work equals 7.02 times 10 to the 10. Whoa. And we discovered that this is positive work. So in order to move it away from the planet from 5,000 to infinity, you would have to do work on the rock. Last but not least, part D. Oh, we're getting low on space. Part D says, what is the work required to move it from from 7.2 times 10 to the 6th meters all the way to 5 was it? Or sorry, to 11.4 times 10 to the 6th. So this was part A, and this was part B. Ooh, interesting. Okay, so doing your equation again, energy initial plus or minus work equals energy final. If we're going from 7.2, that number was negative 1.11 times 10 to the 11 plus or minus work equals this was part B. We got negative 7.02 times 10 to the 10. Adding this number over, we can see that go plus 1.11 times 10 to the 11. You get work equals 4.1 times 10 to the 10th joules. In other words, if you're trying to go from part A to part B, so right outside of Earth's orbit to somewhere out here, yes, you would need to do work because you're going further away from Earth. Earth is pulling you back in. Alright, that's it. Give me any calls, questions, text, emails. Let me know if you have any questions, concerns. That's it. Have a great day.